All right. I'm going to start slowly. I'm going to start with maps. So I think it's the 10th definition of maps of the day, but pedagogy is repetition. So the key point here for me is that maps, they're discrete surfaces. So in a more precise definition is that a map is the data of the gluing of some polygon along their edges to form a surface. So for me, the surface is compact, so no boundaries. It's connected and it's oriented, so not like Maciek right before me. And there's a very important parameter of maps that I'll be interested in for this talk is the genus. So the genus, how does it work? Okay, the genus of the map is also called is the genus of the underlying surface, and it's just the number of handles of my surface. So we've seen a lot of talks about planar maps or maps of the sphere. This is genus 0. This is here is a torus, so it's genus 1, and you can imagine what a surface of any genus is. And yeah, so I'm not going to stay only on planar maps today. Actually, I'm not going to talk about planar maps at all. So this is for maps, and the regime I'm interested in is the regime called hygienist maps. So this is like most of my work is actually about this hygienist maps. As in the talk of this morning, for instance, of Jérémy, we're interested in what does a very large map look like when the size goes to infinity. But for most of the results on random maps, the size goes to infinity, but the topology, so the genus, stays fixed to 0 or sometimes to like a fixed genus. For me, I want to see what a random uniform map looks like when both the size and the genus go to infinity. This is not very well defined, but I'm not going to like do quantifiers of like rate of going to infinity, because I'm going to describe it more precisely only for my model of today. But a thing that's appearing in with hygienist maps, so you can define a notion of discrete curvature on your objects. For instance, by imagining that all your polygons are regular and then with a fixed area. When you fix a fixed area for the total map, if you say the map has to have like total area 1, for instance, and then all the polygons are regular, then, well, you can define some notion of curvature. And in the hygienist regime, the average curvature is negative. So if you have average negative curvature, you can expect some hyperbolic properties. And so that's for hygienist maps, and we already have a few results in this regime. So like one example of this these results is a theorem that I have with Thomas, who's somewhere here, not here, Thomas Budzinski. We studied the local limit. So the local limit, same principle as what Marie told us about this morning. The local limit this time of hygienist maps, and we have very nice hyperbolic local limits. Here there's an image by Nicolas Curien. And so on this hygienist regime, there's still like many open questions that remain. So mostly global geometry of these hygienist maps, also some asymptotic enumeration. So well, yeah, but I'm not going to talk so much about these open problems like in this talk. But hey, I'm here all week, so if you want to talk, I'll be there, and I'll be done with my duties, so very free to talk. Okay, so now I'll make a bit more precise the model that I'm considering in this talk. So I'm going to work on unicellular maps. A unicellular map is just a map with only one face. So if you want to understand what it means, you just take one polygon and then you like glue the edges, the sides 2 by 2, and you get a map. Here, that's an example of a unicellular map. And so my map is a discrete surface, and I'm also going to see it as a geometric object. So I'm going to have a metric, so a certain notion of distance, which is the graph distance rescaled by this factor square root of 12g over n. And I'm going to study this model. Like I'm going to pick a random uniform unicellular map of genus G and n edges with this metric. As the size and the genus go to infinity, and the only restriction, I mean, they can go almost however they please to infinity. The only restriction is that G goes to infinity more slowly than n. So what it means also is that this is going to 0. So like I'm really rescaling this graph not by a constant, this graph distance not by a constant. Okay, so that's for maps. And before getting to the core of the results, I'm going to talk to you a little bit about another model of geometry of surfaces, which are the hyperbolic surfaces. So this is going to be mostly an informal introduction to this field. I'm not an expert at all in the field of hyperbolic surfaces, but I hope it's clear. So what is a hyperbolic surface? A hyperbolic surface is just a surface that is equipped with a metric, so like a continuous metric at each point, such that this metric gives a curvature which is constant -1. So at each point the curvature is -1. In other terms, it means that it looks locally like the hyperbolic plane. All right. And I'm going to talk a bit about some surfaces with boundaries. In the world of hyperbolic surfaces, there's a building block that's very important. It's called the hyperbolic pairs of pens. So topologically, a pair of pens is just a sphere with 3 boundaries. And there's a theorem or fact or whatever that if I prescribe 3 strictly positive real numbers, there is a unique hyperbolic pair of pens with this boundary length given by A, B, and C. And what I mean by geodesic, roughly speaking, it means that it's a curve that is locally shortest path. So you can't like find a shortcut very close to your curve. Okay, so that's for the pair of pens. And more generally on surfaces. On surfaces without boundaries, you can put a hyperbolic metric as long as your genus is greater than 2. Because there's something relating the curvature to the area. I think it's called the Gauss-Bonnet formula. And yeah, the curvature, the integral of the curvature is the area times the Euler characteristic or something. And if the Euler characteristic is not negative, then you cannot have a hyperbolic metric. But anyways, so for any genus greater or equal to 2, this works. And with this kind of hyperbolic surfaces, you can actually decompose them into the building blocks. It's a theorem that there exists a set of simple closed geodesics that divide your surface into a certain number of pair of pens. So basically, these are curves here. They're simple. They don't intersect. And if you take your scissors and cut along them, you just obtain a bunch of pair of pens. So, and the number of these cycles and pair of pens is actually prescribed by the genus. One important thing, though, is that this choice of curves is not unique. This is, well, important to note. And so now we can try to go backwards in some sense. So if I give you this pair of pens with matching, I'm going to try to glue them back together. So I just need to tell you, first I need to tell you the length of the boundaries that I glue together. But I also need to tell you how I glue them together, because I can take two boundaries and glue them like this, or glue them like this. So there's, in some sense, a twist factor. That's just a real that's called tau I. And the thing is, it determines the surface uniquely. So if I prescribe all these coordinates called the Fenchel-Nielsen coordinates, so it describes the surface uniquely. And then you can cook up a space of all the hyperbolic surfaces of genus G. It's called the Teichmuller space. It's just isomorphic to R plus times R to the 3G minus 3. yeah, and that's a space of hyperbolic surfaces. Although the parameterization still depends on this choice of curves. All right. But what we're interested in is actually not the Teichmüller space, is the moduli space. So it's just the moduli space is just the space, the Teichmüller space, so the space of all hyperbolic surfaces up to isometries. So I'm not going to tell you what exactly what is the definition of an isometry, but well, you can imagine roughly what it means. And the problem is that it's not super easy to understand what are the isometries of this Teichmüller space. So, for instance, the Teichmüller space is just a manifold. I mean, it's this thing. The structure of the moduli space, it's not anymore a manifold, because you took like a big space, well structured, and then you fold it on itself with the isometries, and it can have some kind of singularities, so to say. Now I want to put a volume form on this moduli space, and this is a result of Wolpert, that there is this so-called Weil-Petersson volume form, which is expressed very easily in terms of the Fenchel-Nielsen coordinates. Just the product of the dLi, d to i's. And this is a volume form on Mg. And so this result has been called like magic formula, because there's plenty of magic things happening. First, it doesn't depend on the choice of curves. So the coordinates, the coordinate system depends on your choice of curves. There's nothing canonical, but when you go to this volume form, it's actually independent. It's invariant under like the action of the isometry group. Also, this is well defined on the Teichmüller space, but it descends on the moduli space. Still, it commutes well with this quotienting by isometries. And for us, the most important thing is that if you take the integral of this volume form over the whole moduli space, it gives you a finite amount. And when you have a finite volume of something, then it gives you just a probability measure, because the measure of a subspace of your space is just the probability measure. The probability of your subspace is just the volume of your subspace over the total volume, which you cannot do if you have an infinite total volume. And this is, for me, this is also one of the reasons why we care about the moduli space, because maybe you think, why would we think of something that's more complicated, where you have the Teichmüller space is well described, it's very nice structure, but unfortunately you can see very easily that it has infinite volume. So at least from the probability point of view, it makes sense, because now we quotiented this thing into a finite volume space. And then we can do probability. So what it implies is that we can sample a random hyperbolic surface under what we can call the Weil-Petersson measure. And it turns out that this SG, so for each genus you can sample a random hyperbolic surface. And some people 10 years ago started to think, oh, what about the properties of this hyperbolic surfaces when the genus goes to infinity? So this has been independently introduced by Mariam Ezahani and Gut, Parley, and Young. I think both the exact same year. Yeah, so there's a bunch of geometric results. I'm not gonna like make an overview, but like all the geometric observables you can think of, diameter and size of some cycles have been investigated. And now I'm going to get to like the precise problem that I considered with Zonte and Son. And now I am in my work, I'm interested. So going back to my model of maps, or the model of random hyperbolic surfaces. So this is a model of, yeah, just a model of random surfaces. And I'll be interested in counting short, simple closed curves. So, well, I think everything makes sense. So short, it just means that it has a constant It's a constant length. Simple, you know what it is. Closed, you know what it is. And curves, I just need to make it a tiny bit more precise depending on the model, what curves mean. But here's a surprising coincidence. So a few years ago, Mirzahani and Bram-Petry studied the number of simple closed geodesics in the random Weil-Petersson surface, hyperbolic surface. So they count the number of simple closed geodesics that have a length between x and y, fixed x and y, as the genus goes to infinity. And this is a random variable because they have random surfaces. And I have shown that this converges in distribution to a Poisson law, which has this parameter, like this integral of the hyperbolic cosine. And what we did with Svante Jansson is we studied a different type of curves, simple cycles in our case, in the model that I told you about. And we obtained the exact same result, like the exact same convergence. So here the length, you must remember that it's the graph distance rescaled by something. So this makes sense to have a continuous interval and not a discrete interval. And it converges to a Poisson law of parameter, the exact same parameter as Mirzahani and Petry. And in both papers, there's actually a bit more than this convergence. It's for those who know, it's a Poisson point process convergence, which means that if you take several disjoint intervals, you have a convergence to independent Poisson variables. But that's just mostly a technical detail. And so this is a coincidence, but is it really just a coincidence? I mean, I cannot say for sure it's not just a coincidence, but I mean, I want to have faith and I want to explore it at least. And it's not totally absurd to think there's a relationships between these two things, because there's two models of geometry of surfaces in high genus. So roughly speaking, our conjecture is that those two models, as the genus goes to infinity, they're the same. So I mean, this is very vague, but yeah, you need to have a well-chosen metric and so on and so forth. I'm not going to give you a very precise, super precise conjecture. And one of the main reasons for this is that it's a bit hard actually to make a really precise conjecture because it requires some work. But we've identified a few key points at least. And then it's going to also explain why this conjecture needs to be refined a bit. The first thing is that we need to remove the fractal part. So if you look, this is what a unicellular map looks like. You see it's like it looks like this thing, like a very regular thing, like what we call the two-core. And attached to each point, there's each vertex, there's like dangling trees. The dangling trees, this is the fractal part. This is the Brownian bit of our maps. And the problem is that the hyperbolic surfaces, they're very smooth. It's constant curvature. And as you have seen, for instance, in the pics that Jeremy showed us, maps are anything but smooth. So you need to get rid of this fractal part. But you can note that in our case, when we were counting simple cycles, well, we didn't care because a simple cycle is never going to go through these trees. So taking the map or its two-core is basically going to be the same. And so alternatively, you can also think of maps with all the vertices at least degree 3. And instead of having vertices of degree 2, you think of edges with some lengths on them. And the other important thing is that as it is, so far our map is like, if you just look at the graph locally around a given point, it just still looks like a graph, even with the rescaling. Because the cycles, there's no microscopic cycle. So it's very different from the Brownian map point of view, where there's a lot of microscopic cycles and this discrete object becomes a continuous one. But the good news is that we define our unicellular maps as a gluing of a polygon. So why not define just these maps as the gluing of a hyperbolic polygon? And this is also like a reason why this conjecture is not yet super precise, is that I didn't specify which hyperbolic polygon. Because if you glue a polygon, any polygon, if the angles don't add up to like 2 pi, you might have singularities. So there's many ways of dealing with this. Either this is, well, we need to find the perfect polygon that fits super well, or there's like a procedure, like if you have a map, that surface that's exactly hyperbolic, except for some points, you can like cut and then really, smooth, and I don't know the procedure, but the name of the procedure, but it's been used in models such as like Brooks-Macover. But anyways, so there's still a bit of work to do on the conjecture, but my belief is that, well, in some sense, this conjecture has to be true, and that the precise version, we will have it basically when we prove it. As we advance on this conjecture, we will know what are the requirements. I mean, if everything is true, we'll find out while proving it. And just a word about the notion of metric. I'm thinking the right metric is the Gromov-Hausdorff distance on metric spaces. And I'd like to have something a bit stronger to make sense of the topology. For instance, the separating curves, if you think of it, it's not encoded in the Gromov-Hausdorff point of view. And well, counting, for instance, the separating systole, which is the size of the smallest separating geodesic or separating curve, separating non-contractible curve, it's an important problem in geometry. So like Gromov-Hausdorff distance would not encode this. Sorry.
When you say the metric space is
no, with the hyperbolic polygon. Otherwise, it's not possible. It wouldn't work, because then the geometric space would look like a continuous graph. Because there, as I said, because there's no microscopic cycles. So I mean, this. I'm going to show you again the theorem. Actually, it's not. You cannot really guess it from the theorem, but the theorem is also true like as you approach 0. So it also means that with high probability, you don't have like cycles that are of order smaller than this square root of g over n, which is the difference with the Brownian map. For instance, the Brownian map, the cycles are like the face is like quadrangulation. So this is going to disappear in the limit and like make a very like thin meshing of your surface. Does that answer your question? Okay, well, okay. All right. When did I start? At 30 minutes ago, right? Including questions, right? Not including questions. Oh God, I went a bit quickly then. That's fine. Okay. I need to slow down then. You paid to be here until 6, so you're gonna be here until 6. No. But I mean, yeah. Oh yeah. But I'm not done anyways. So. I'm going to make a reference to Jacopo's metaphor of this morning of the bridge. So this conjecture, if true, it's nice. It's a bridge between two worlds, and it kind of contributes to this idea of universality. So that meaning that they have different models of geometry of surfaces, and they have like similar behaviors. And well, if the conjecture were true, they would be like kind of very rigorous. But it's not only for the sake of it for the sake of the bridge, of building the bridge. So I want to use the bridge, as Jacopo said. My hope is that the conjecture is true, and if the conjecture is true in a strong enough sense, basically you can transfer any, in the large genus limit, you can transfer any geometric problem. Well, not any, depending on how strong your theorem is. But you can transfer problems from hyperbolic surfaces to large genus maps. And the good news is that large genus maps, at least the unicellular large hygienist maps, we know how to deal with them very well, because there is a very beautiful bijection putting these maps in bijection with trees. So then you have hyperbolic problems and you transfer that to problems of random trees. And I guess all of you here know that problems of random trees, we really know how to tackle this. There's like thousands and thousands of papers about it. So hoping, like, assuming everything goes well, we might have use like random tree techniques to prove things about hyperbolic surfaces in large genus. And I mean, we don't have to wait for the conjecture to be proven to start working on the equivalent model. So at least to see if this also could give us some directions and ideas about like adjustments to make to the conjecture or what to prove or anything. So I'm going to give you two problems that are open in hyperbolic surfaces. The first problem is the diameter of the hyperbolic surfaces. It's been proven that the diameter is of order log g. So there is a deterministic area argument that says that it has to be at least log g up to smaller order terms. And some spectral arguments prove that it's at most 4 log g. But as you know, as in random graphs, we think that, I mean, it's not absurd, completely weird to think that it's concentrating around some constant times log g with high probability. So yeah, so like the question is, what is the right constant? And well, the opinions of the experts vary. Some people say it's 1, some people say it's 2. And I've never heard anything else than 1 or 2. 3/2? Yeah, I'm not sure. Anyways, so that's for the first open problem. There's also, we can also ask for spectral properties. So there is the spectral gap, which is basically the value of the second eigenvalue of the Laplacian of the surface or of the graph in case of the maps. Also, like the Cheeger constant, which is related to the expansion properties either of the surface or of the graph. So that's it for the open problems. And in the remaining time, I'm going to give you some ideas of the proof of this result on maps. And I'm going to start with the magic bijection due to Chapuis, Ferret, and Fusy. So Guillaume was here, and Eric was here, and Valentin who's not here. So let me define the model of tree I'm talking about. I call, it's not me who calls these trees like this, but they're called C-decorated trees. So for the experts, I'm going to use a slightly different definition than in the original paper. For me, a C-decorated tree is a tree with a permutation on the set of its vertices. And the permutation has to have only odd cycles. So here is an example, and you can guess which condition I omitted because I stole the picture from Guillaume and I forgot to remove. The signs are not supposed to be here. They were here in the original definition, but we don't need the signs for our proof, so we make our lives easier and we forget the signs. So this is the model of tree. And the thing is, you can build a graph out of this tree by taking the vertices that belong to a same cycle and just like merging them, like you continuously merge them, so you bring them together. And so this C-decorated tree has this underlying graph, for instance. So the red cycle is going to merge into this big red vertex, and so on and so forth. The only thing is that this tree here, it's oh, I forgot to say, I'm talking about trees who are planar and rooted. So they have this geometric structure, this like clockwise structure around the edges, around the vertices, sorry. Here, the underlying graph has just a graph structure. We don't know its map structure. And, oopsie. The tree, it's a planar rooted tree. Yeah.
But then you forget about it.
Yeah, you forget. Yeah, it's. This is the underlying graph. So now I'm going to take a random uniform C-decorated tree, and I'm going to define some notion of genus on this tree. I'm just going to say T and G is the random uniform C-decorated tree with n edges and n plus 1 minus 2g cycles in the permutation. Or equivalently, its underlying graph has exactly this many vertices. All right, and the bijection of Chapuis, Ferré, and Fusy in the probabilistic version of it is that the law of the underlying graphs of the unicellular map, U and G, I remind you that U and G is the uniform unicellular map with n edges and genus G, and this T and G. So the unicellular map, the underlying graph of a map is just the graph when you forget the geometric structure, by the way. So this, the bijection tells you that these two underlying graphs have the same law. And this is, I mean, this is a very powerful bijection, and there's been like a couple papers on hygienist unicellular maps, and if I'm not mistaken, almost all of them, but for the exception of one of them, use this bijection as a key tool. Like that's the most important bit of the proof. And here, in our case, we're going to use this bijection because we're counting cycles. We don't care so much about the geometric structure. We just need the underlying graph. And the key point to count cycles is just to understand what is a cycle in the underlying in the C-decorated tree. And if you think a bit about it, a cycle in the underlying graph of your C-decorated tree is just a list of paths such that the endpoint of the first path is going to be merged by the permutation, so belongs to the same cycle of the permutation, to the start of the second path, and so that the end of the second path is going to be merged with the beginning of the third path, and so on until you reach the cycle. So here I draw an example. So it's very schematic, but so this is a tree, this is 3 paths, and these arrows just indicate that these 2 vertices are going to be merged by the permutation. I say they're going to be merged by the permutation because I don't want to say they belong to the same cycle of the permutation, because there's 2 notions of cycle and it's a bit annoying. So if I do a partial merging, I don't care about the rest of the underlying graph. I'm just going to merge these vertices. Well, you see that this forms a cycle. I'm cheating a bit here because I'm counting simple cycles, so they cannot self-intersect. But I'll leave this to you as an exercise to find the right notion. But this is the most important part, and then the rest is just technical details. Once you get this, you can define cycles, and then you can find out what the extra condition for having a simple cycle is. So this is with this magic bijection. Now we understood that to count cycles, we need to count basically paths in trees. And counting paths in trees, it's very standard. We can do it quite easily. And I think there's more than one way to do it, but I want to count these paths with analytic combinatorics. So to count paths in trees, I'm just going to count trees with a marked path on them. And so how do you build a tree with a marked path on it? Well, you just take your path, take as many trees as needed, and you graft your trees at each of its corners by its root. So as simple as this. So if the path has length L, you need 2L trees. And so the analytic combinatorics and symbolic method tells you that, well, the number of, if you want to count the expectation of paths of size L in your random tree, you just have to count the number of trees with a marked path and then divide by the total number of trees. So this is the total number of trees, Catalan of N. This is the generating series of a sequence of 2L trees. You take the right coefficient so that it has the right size. You multiply by this 2n because you need to have a root. I didn't talk so much about the root, but I think the others define what it is, so I'm good. And you calculate, and you get this. This is equivalent to 2nl. And actually, what we do is also we do the second moment, and then with the second moment method, we have the strong concentration. So L2 convergence of this thing, well, L2 convergence of this divided by this to 1. There's a bit of well, technicalities here, because here this L goes to infinity. We're in this regime where L is smaller of root n, because we're counting cycles that have constant size, but in the graph distance rescaled by something, well, divided by something that goes to infinity. So you need to count paths of a certain size that go to infinity. And fun fact, for those who know analytic combinatorics, when you have like this bivariate thing with this nice expression, you're tempted to use the saddle point method, but it's not exactly the right regime. You don't have the right, like if you redo the proof of the saddle point method, you see that you're not allowed to do it, but surprisingly enough, it still gives you the right answer. That's also an open problem for those who know the saddle point method. Why does that work? But you need to prove it a different way. You cannot use the saddle point method. Okay, and then when you to finish the proof, I'm gonna say it very roughly. So you can prove that you can pretend that your permutation only has cycles of length 1, so fixed points. So vertices are not going to be merged, or cycles of length 3, so like just 3 vertices get merged. And in this case, you have G of them. So this is not exactly true, but what I'm saying is that you get moments of numbers of cycles. You get enough moments so that you can basically everything works as if there is no cycle of length 5 or whatever. I mean, there is cycles of length 5, but you're just not going to see them. And then, oh, interesting. Okay, then you can calculate the probability that 2 vertices get merged by a permutation. So I hope I didn't make a mistake. So there's G cycle. So if 2 vertices, so basically you can think of your cycles of length 3. 2 vertices are going to be merged if they belong to the same cycle of length 3. So you can think of your 2 vertices as balls and your cycles of the permutation as boxes, and then you're going to throw them inside the boxes and you try to estimate the probability. So there's G boxes, and for each box you have well, this probability of hitting the box. So you want that both vertices hit the box. So this gives you the probability that 2 vertices get merged by the permutation. So now if you have a list of k paths and you have the endpoints, you have like k mergings to make. It gives you roughly this thing. So it's not exactly independent. I'm doing as if it's independent because enough moments to pretend it works. But roughly speaking, the idea is this, and then you just need to sum. Like the expectation of the cycles of length L. So your cycle of length L in the tree is going to decompose into a certain number of paths. This is k. And then you're going to sum over all the possible lengths that sum to L of the probability that it works times This is the estimation of the number of paths. So we have strong concentration. Again, there's a trick because you want your cycles to be simple. So you also want to prevent that other vertices of the cycle are not going to get merged together. But it turns out that it doesn't matter. Like it's just a small O of one factor. And so if you sum all this and you do a bit of calculations, you obtain this as the expectation. And the Poisson law is something quite classical in random graphs. It boils down very roughly to say that with high probability, you take two cycles. If you condition on the fact that they are distinct, that they're not the same, then they have to be disjoint. So yeah, so to emphasize the coincidence was not that we had two Poisson laws for our models. The coincidence was that the parameter of the Poisson law was exactly the same. Okay, and oh yeah, just to finish with some additional questions. Is there questions on the proof? I think we still have like some time. No? Okay, good. Just two additional questions to my set of questions. Yeah. Yeah, so I mean, I just roughly explained the principle, but in the end, when one cycle or two cycles, you can still two cycles, you can still say what it is. It's like it's two sets, two lists of paths such that the endpoints are merged, and then that individually it doesn't like collapse on itself so that it doesn't make a non-simple cycle. And then you can, I mean, it's purely technical at this here. Yeah. Well, I don't know exactly what it means, asymptotic independence, but I'm just what it means. What I know is that when you make the calculation, the contribution of the pair of cycles that intersect is basically zero. Not zero, but like smaller of one compared to the rest. And then, well, you do it for all the moments, and you're good.
You have to do it for moments, or you can stop it?
Yeah, I know. So I'm aware that there's this thing called the Steinchen method, but I think you need a very precise control on the variance or something like this. I think there's. So I'm not an expert. I know it's. So we used just the method of moments because once you can know how to do two cycles, you know how to do basically any number of cycles. And you just need to show that the variance is smaller of the expectation of the square of the expectation. Whereas I guess in the Steinchen method, you need to be more precise with your estimation of the variance. I'm not so sure.
You are just with your version where you have to show the variance.
Yeah, but it doesn't. Like the. I don't think having just a small variance shows you that you have Poisson. I think you need extra conditions. I mean, I think.
This is what you're doing.
What I'm doing is I'm showing the variance, but I mean, yeah, okay. When I say this, I say any finite number of cycles have to be disjoint. I'm lying a bit, but I'm just wanted to extract the like substantifique moelle of the idea. But yeah, it's any finite number of cycles.
When do you compute? You wrote expectation of cycles of
No. Yeah, here I just computed the expectations. The expectation. So now I know the expectation.
You want more time.
Oh yeah, of course. Like there's. It's just that it's just technical. It's very like it's annoying to do. It takes like 10 pages, but then you just compute. You just write out what it is to have a list of this many cycles that have this list of length, and then you. Yeah, we were computing all the moments.
All the moments for
the finite moments. Yeah.
The parameter of the loop, you have a random lead, right?
Yeah. No, yeah, I mean, I don't know. So, like, to prove Poisson convergence, there's something called the Steinchen method, which I just know, I'm just aware that it exists, but I know you just need 2 moments, but more precise, because you don't get it for free. And I think that this is what you were referring to, maybe, or maybe I just misunderstood the question. Yeah, I just use the moment method. Yeah, basically. That's fine. Okay, yeah, that's.
You want to show convergence to a point process, so you are computing the endpoint correlation of.
Exactly. Sorry. Yeah. So this I don't know. Yeah. So yeah, you show the endpoint correlation, or like the multivariate moment, if you want. Yeah. We just use the multivariate moment method, but everything works. Like once you know how to do it for 2 cycles, you know how to do it for multivariate moments, because we just need finite stuff, like finite number of so it's endpoint, but n finite, and you just need the finite moments. Okay, I didn't understand this was your question. Okay, I'm going to get to the additional questions now. There's 2 more questions that I want to ask. So I know that Timothy and Nicolas here, they've also worked on hyperbolic surfaces, but the hyperbolic sphere with cusps. So I was lying when I said you cannot put a hyperbolic metric on the sphere. If you have like this infinite spikes, you can, because it augments the Euler it reduces the Euler characteristic, so you're good. And they implemented they introduced the equivalent of the Scheffer bijection on this hyperbolic sphere with cusps. And my question is, can you do the same with the Chapuis-Ferré-Fusy bijection? Can you work out something for surfaces of genus G? I mean, we've seen how powerful it is for maps. So that would certainly be very interesting in the case of hyperbolic surfaces. I don't know if this question makes sense. I'm just throwing the idea. The other thing that I'm thinking about is that if you take this time a different space of hyperbolic surfaces, so it's hyperbolic surfaces with 1 boundary, geodesic boundary, and so you fix the genus this time, and if you take the size of the boundary to go to infinity, basically what you're going to have is a map with 1 face. And the reason for this is that the area has to stay constant because of the Gauss-Bonnet formula again, and so the boundary is gonna be huge. So it's gonna crush the rest. Like it's gonna be very long. So to have constant size, you're gonna have like very thin strips, and in the end, you're gonna get a map. So a metric map. So if you do a proper rescaling of the geodesic distance, you get a unicellular map because there's just 1 boundary, so it's 1 interior, and you get real edge lengths. So same question: is there a connection with our setting? And maybe my conjecture is not true for maps without boundaries, but it's true for maps with a boundary in the right regime. I don't know, but I wish there's a connection between these 2 worlds. And yeah, now I'm done. Thanks.